All right. Welcome everyone to today's class. This is session 17, week 9. All right. We are rounding up. This is the third month of the program. Right. This is actually the third month of the program. We had the first month, which was in July. Then we started July, then August, which is ending today, and then um, we're entering September by God's grace tomorrow. So you've actually tried sticking up to this point, and that shows how committed you are to this, and I assure you that you would definitely benefit a lot from this program, and you won't regret giving your time to this. All right, so yeah, there are quite some things I will need to talk about before we go into the class today. So first off, I will talk about the assignments. All right, so the assignment was I've graded the assignment for everybody, so everyone should have seen their grades for week 7 assignment and week 8 assignment. So this week assignment has actually been graded. So if you check, you should have received a notification by now, um, um, showing you your grade and all of that. So in case you have any issue or complaint or whatsoever, you can just can let me know. All right, you can let me know. So I'll see. We'll look into it and see what the issue is. So for the previous assignment, which was week 7 assignments, now I would have to talk about that. Now, a lot of us were actually complaining of a similar issue, which was that you did the assignment right on the Google form and you got your score, but when I returned your grade, you were seeing 0. Now that's actually from your own side. It's actually your fault because I graded it based on the class, the different classes. That was why I asked you in the Google form to indicate your class. All right, I asked you to indicate your class there because while I'm grading, I filter by class and then input the score from the Google sheet, from the score sheet, right? So if I don't see your name in a particular class, it will be assumed that you didn't respond to the question. All right, so the class you filled on the Google form has to correlate with your class on Google Classroom. So if you didn't put it correctly, then you definitely not get a score. So that is why you are actually having this issue now, right? So I think somewhere I don't know why till now some of us don't know our class. I actually made sure I told us all about this initially, except you missed those classes. But um each person here belongs to a particular class, right? We have 10 classes here. So you belong to a particular class. So once you go to Google Classroom, you see the name of your class there, whether it's Data Gene or Detectives or Pythonista or what have you. So you make sure you note the name of your class there. So whenever I'm asking you for your class, you just tell me and I can go back to the Google Classroom and resolve your issue. All right. So whatever problem you had from the Google form, just know it was from not following the instruction or not filling your information appropriately. So, but that's not an issue. I've already requested that everybody that was affected should indicate their name on a list. So once I compile that list, I think today is going to be the deadline for that. Once I compile that list and I resolve and give grades to everybody affected, I'm not going to attend to any other person again. All right, I'm not going to attend to another person because I have a lot of other things to do, and I'm trying to make sure that everybody is carried along, right, and you don't miss your mark because of some oversight. So that is just it about the assignment. Please let's try as much as we can to follow instructions. So still talking about assignments, we are going to be ending assignments. So I'm going to stop giving assignments next week. All right. So after next week, we are not going to be getting any assignment again. So we actually shift our focus to the project. So the project would actually be talked about by week 10. All right, by week 10, after Sunday's class, we're going to talk about it, and you're going to start the project. So the project will be lasting till the end of the it's going to last to the end of the program. That is, I think you'd have 2 weeks for your project, 2 weeks plus. So after the deadline, as I said initially, that there would be a project defense where you come and after upgraded you come and actually defend your project, right? And to be certain that yes, you actually knew what you did this project yourself, and you understood all the things that were in your project. So these are the things that we're going to be doing moving forward. So we still have a lot to do going ahead. I think the end of the thing is better than the beginning. So you've come this far. Don't allow yourself to become weary. Don't allow yourself to start to um, slack. All right. So I trust that you're going to keep up. You all are going to keep up to the end. So today, can everyone still hear me clearly? Please let me know. Can everyone still hear me clearly? All right. Okay, that is it about the assignment and the project. So right, I've talked about the video issue. I've uploaded another video for you. I've talked about the feedback form. I've talked about the assignment and all of that. So now we're quickly going to go into today's class. But before we do that, I'll just quickly go over the assignment. Right, we actually started late today, but it's all right. At least we achieved what we wanted to achieve. All right. So as you can see on the screen, we have one of the assignments. I think it's a class work assignment. So I'm going to be using this for correction. Right. I'm going to be looking at the answers and where most of us actually missed it. Because I'm going the assignment, I saw that some of us we actually didn't understand some of the questions. So it's necessary that I put us through all of that. Okay, so I gave us 5 questions in the week 7 assignment. All right. So the first question was I gave you a video. I attached a video to the assignment. So you have to watch the video before you attempt this assignment. So for those that didn't watch the video, um, all right, sorry for that. For those that didn't watch the video, I don't know how you would you planned to answer the question or you answered the question. Okay, let's just move ahead. Oh, the first question here was for you to list 5 differences between linear regression and logistic regression from the video. All right, so this one I actually expected everyone to get it, so it was not really much of an issue. So you already know the differences between these two machine learning algorithms. One predicts continuous variable, the other predicts categorical variable, and all of this. So I'm not going to go into this because of time. So question 2 here is where most of us actually, question 2 and 3, where most of us missed it here. So the question is, the linear regression use case mentioned towards the end of the video is what type of linear regression. All right. So I think the reason why some of us failed it was because we didn't understand the question. So what I'm asking is, remember I taught us the different kinds of linear and logistic regression. So I was asking you what type of linear regression was used in that particular part of the video. All right, in the example that was given there. So use case is an example. Can everyone hear me? Please let me know. Can everyone hear me? Can everyone? All right. So, Peter, please check your network. All right. So I gave us examples of linear and logistic regression. So that is basically what I was asking in this question. I needed you um, let me know what type of linear regression and logistic regression was used. Some of us were saying different things, right? Some were even saying positive correlation. Some were saying a lot of things that are actually not the answer. The answer here is what simple linear regression. All right. So if you watch the video, you know that it's just simple linear regression because there is one dependent variable which is monthly sales and one independent variable which is online advertising cost. All right. So you can see the explanation here. So the same thing goes with to number 3 question. What type of logistic regression was used? All right. So the answer is binary or binomial logistic regression. Okay, binary or binomial logistic regression. So this is just what I wanted from these 2 questions. So the other questions are actually giveaway questions. Mention 2 new points learned from the video. And still yet, some persons, just few persons, you just said you learned machine learning. Some said you learned classification and regression. That is actually nothing, right? You can't tell me that you learned machine learning from a video. It's not elaborate enough. So you don't answer this kind of questions like that. You tell me exactly what you learned. If you learned machine learning, what part or what aspect of machine learning did you learn? All right, machine learning is too broad for you to just say you learned it. So outside this video, the last question was for you to mention 2 extra use cases of linear regression and logistic regression. All right, so there are a lot of examples that you can pick from, a lot of them. So I love how elaborate this answer was. All right, so you know what linear regression is used for continuous variables and logistic regression as well for categorical variables. Still yet, some of us we were not really specific with our answer. Some said disease prediction. What is disease prediction? Or is it to predict disease? Like the answers were not specific. You need to be specific. Okay, what exactly are you predicting? Are you predicting that the disease is present or not? Or are you predicting the type of disease that is there? Right. So you need to learn how to answer questions. Right. So you develop yourself better as a data scientist. So these are all the things we are doing in this program. It's just to help you all around. All right, just to develop your comprehension and question answering skills in relation to data science concepts. So this assignment was just about that. It's actually not very technical. So I believe we've all seen our grade by now, and we've taken correction as well. All right, so that's going to be it. We are not dwelling much on this assignment. So just take note of where you missed it, and and you would make sure not to repeat it next time. So we are going to be going into what we have for today. So today we are going to be looking at other machine learning algorithms. All right, we are going to be exploring other types of machine learning algorithms. So today and tomorrow we are going to be exhausting the algorithms that we will be looking at for this program. So we started with linear regression last week, and then this week we looked at we started with linear regression and logistic regression last week. Now today we're going to be looking at 3 other algorithms. All right, we've shown you how to implement linear regression and logistic regression in Scikit-Learn. All right, how to get your data set, how to split your data set, how to train your model, and how to evaluate your model. So you already know the steps of building a machine learning model. So that's a general overview. That is actually an overview of approaching machine learning problem. So today we are going to be introducing newer algorithms or new algorithms that you can also use in performing or carrying out the same task. All right. Remember, I told us we have regression task and we also have what classification task. So we have aside linear regression and logistic regression, we have other machine learning algorithms that we can use to perform classification tasks as well as what regression tasks. So today and tomorrow we're going to be using it to look at all the other kinds of algorithms. We're going to be looking at k-nearest neighbor today. We'll look at support vector machine, and we're also going to look at decision trees. Moving over to tomorrow, we're going to be looking at ensemble techniques. All right. So tomorrow we're going to be looking at random forest. We're going to be looking at boosting algorithm. We're going to be looking at bagging algorithm. We're going to be looking at XGBoost. So by the time we go over all these algorithms, you can now know which algorithm to select for your particular problem. All right. So there are some particular data sets that will require that will work well, right, with a particular algorithm. You understand? There are some ones that will work. So these are the things you just need to know. So you have options to pick from, right? Moving over to next week, we are then going to look at how to pre-process our data. All right, we're going to look at pre-processing our data. We're going to look at other techniques in Scikit-Learn that we can actually use and develop from there and see what we can actually do. So trust me, in 2 weeks' time, you'll be able to actually view the machine learning model from start to finish. All right. So, but I'm still looking at there was something someone raised in the last class. Someone raised in the last class asking if we're going to be learning how to deploy our model. I actually thought about it. All right, I thought about it, but looking at what we have, it's not part of the curriculum actually, but I'm going to see if we can finish all what we need to finish on time. Then we can dedicate 2 classes into looking at how to use Streamlit to deploying something, an app is actually it involves a lot of things. All right. It involves you creating a front end, it involves you creating a back end, it involves you doing a lot of things. But there is a particular library in Python that can enable you, or that would help you to just package what you've done in an app and present it. All right. You can as well even deploy it on Streamlit Cloud, so anybody can actually access what you are doing. So if you do that wherever you are, and you send the link to the group chat, anybody can open it and look at what you've done. All right. So it's actually going to be very interesting. But I'm going to try as much as I can to see if we can learn Streamlit. All right. So if we can just implement, if we can do that. But if we don't get enough time, then I'm going to send a link for us, so we'll look at how to use that. Okay, so that's it for that. Just have all this at the back of your mind. Just know that these are the things we are still going to be doing. So we've done a lot, right? We've actually come a long way. All right, we've come from Python basics and all of that. We've looked at libraries. We looked at pandas, NumPy, Matplotlib, Seaborn, and we're currently looking at Scikit-Learn. So you've actually gathered a lot of skill, all right, during the course of this program. So please don't throw this away. All right, don't throw this away. This is a very, very important skill you are getting from this program. All right. If there's some things you've not understood yet, well, you have enough time. Like during your project period, we are just going to be having classes. We are not going to be giving assignments. So what you just have to do is just focus on your project and then recapping on everything that we've done so far. So you should have enough time to be able to go over them. I just need you to to by the end of the program, you should have been able to, you should at least have a very good ground. You should have a very solid foundation on all that we've done. All right. So if anybody asks you question regarding anything we've done, you should be able to answer them. You should be able to answer them. As I said before, there was a particular student in my previous class that immediately she finished this program, one of our colleagues in our workplace referred her to someone, and the person they told the person that she actually is a data scientist and all of that, and that was her first time. She had no prior knowledge in data science before entering this program, so it was through in the course of this program that she was able to build herself and gather enough skill. All right, and she got a gig from them, like to actually build a machine learning model and deploy it as well. All right, so and she took it up. So that's actually a challenge. So there's if you look at the difference between yourself when you started and now, you see that yes, you've actually the difference is glaring. Difference is actually there's a huge difference. So please and please maximize what you are learning from this program. If you are to go into any platform to learn data science as you are learning like this, where you have live classes, trust me, you're actually going to pay a lot of money. You are going to pay a lot of money, particularly data science. Particularly data science, and most time you don't really get to stay for about 3 months, right? So you should understand the value of what you are getting from this program. So I just want to take some time to let you know that this program is giving you a lot, and don't take it for granted. That is just a summary of what I'm saying. All right, so enough of all of that. Let's just go into what we have for today. Okay. So today we're going to be looking at other machine learning algorithms. All right, we're going to, as I said, we're going to look at k nearest neighbor. We're going to look at support vector machine, and we're going to look at decision tree. So we are not going to go into details, into the mathematics and all the nuances of this algorithm. But I'm just going to give you an overall intuition, like an intuition of how this algorithm works. All right. So maybe after this class, you can now go further to understand the mathematics and all the details and all of that, right? Because there are also some things that there's some mathematical concept behind them. All right. But what you just need to know is how do these algorithms work. The same way we looked at linear regression and logistic regression, same way we looked at how linear regression uses a regression line that gets the best fit which minimizes the sum of squares error. All right, and then that is the relationship. That is the perfect relationship between the input and the output. So that is the model. That is basically what linear regression does. We also looked at logistic regression, which is an adaptation of linear regression, introducing sigmoid function, right? The sigmoid function takes an input and what maps it to probability values. So that's also the intuition of logistic regression. We looked at all of that. We're going to also look at the intuition of these other algorithms today. God willing, we finish up with them and we move on to the next one tomorrow. So I just want us to finish all these algorithms today and tomorrow. Then next week we move on because there are other things that we need to learn in machine learning. All right. So now we are going to first look at k nearest neighbor. K nearest neighbor algorithm. Please, can everyone still hear me? Let me know in the group chat, please, if everyone can still hear me clearly. All right. All right, perfect. So k nearest neighbor, what's k nearest neighbor? K nearest neighbor is, let me zoom in a little bit so you see it. K nearest neighbor is a simple, intuitive, and what versatile machine learning algorithm used for both classification and what regression task. All right. So I would actually say that k-nearest neighbor is a very simple algorithm, and it's there's something that differentiates it from other algorithms that we've looked at and we are going to be looking at. So we're going to see it as we are moving forward. Okay. So okay, yeah, thank you. I think everyone can hear me. So yeah, let's just move on. So as I'm saying, k-nearest neighbor is a very, very simple algorithm, right? Very, very simple algorithm, and it is called what it is known as a lazy learner. A lazy learner. Let me create a new file here. Okay. So KNN, K nearest neighbor, is what known as what a lazy learner. Why? Because let me just put this in. Because it doesn't learn anything during training. All right, so I just wanted to put this out here. So KNN is known as a lazy learner. It doesn't actually learn anything during training, unlike other algorithms that we've looked at. So um, other algorithms actually looks at your data and tries to map out the relationship in your data, trying to get the connection and also learn different values that would affect the impact of your independent variable on your dependent variable. So we've looked at that previously. Now, KNN doesn't learn anything, and we are going to see exactly what we mean by that. But just keep that at the back of your mind. So as we've seen here, it is used for both classification and regression tasks. So these three algorithms that we are looking at today, KNN, SVM, and decision trees, they can actually be used for both classification task and what regression task. Unlike linear regression, so linear regression can only be used for what regression task. Logistic regression can only be used for what classification task. So linear regression and logistic regression, they are usually considered as a twin algorithms, all right. So they're usually considered as brothers and sisters. So but for the other ones we're going to be looking at, they actually can do the two tasks. All right. So you can actually use them to perform classification and also use them to also perform regression. You'll see that as we move ahead because we're actually going to do implementation today. We're actually going to write code to show you how all this thing works. So okay, let's look at this. So that is basically what KNN is. It's a type of instance-based learning where the algorithm makes prediction based on similarity. Now, this is what I need you to pick here. Similarity, based on similarity between the input data and the stored instances in the training data. Oh, these are all sounding like jargon, but just follow me here. It's going to make sense as we are moving forward. The core idea of KNN is that similar instances are likely to have similar outputs. Similar instances are likely to have similar outputs. So it's just like birds of the same feather flocks together. So if you see a group of birds, all right, flying together, and you see one other bird, let's say you don't really know what that bird is, you've not be able to identify that bird species, all right, but you now saw that bird flying together with those other birds that you already know. You already know that these birds are actually this particular species, all right. But the one that you just saw, you don't really know the species, but you now saw it flying alongside with these birds that you know, what will come to your mind? You would automatically tag this new bird that you are seeing, right, as the same species with these ones here, right? That is what we call birds of the same feather flocks together, right? You just categorize all of them as one because they're in the same group. That's actually the core idea in KNN, right? K nearest neighbor. Nearest neighbor is what I just explained now. I'm going to explain what K is. Okay, K basically is referring, okay, we'll look at that. Let me just move ahead. But this is just the idea behind K nearest neighbor. So this is an illustration, a diagram to illustrate what the algorithm is actually doing. So for instance, let's assume we have two classes. This is for classification basically and regression, but we are going to just explaining it on for classification mostly. All right. The regression aspect is just an adaptation. All right. So let's assume you have two classes in this case, right? You have two classes. You have the red class and the blue class. Now, what happens? Nothing happens during training, right? The data is just as you can see here, they are just distributed, all right, according to their values. So let's say you now introduce a new data set. You can see the new data set, the new data points that you want to predict, all right? For example, the new bed, the new bed that you don't know the species, but you want to actually label it. So this green dot here is the new data point, all right? And you bring it into the, you place it or you map it based on its value in the, in this particular space, all right? In this particular space, all right? So now, based on the nearest neighbors, on the data points or the classes that are closest to it, you will now determine the class of this new data point. So that is where this K come in, all right? This K that you can see here, K basically means the number of neighbors, all right? The number of neighbors. So in this case, if we say we're going to use K equals to 4, so we're going to use 4 neighbors to determine the class that the new data point will belong to. We are now going to, from this new data point, we are now going to look at the 4 closest data points or the 4 closest classes. So in this case, if we look at the 4 closest classes, we see that we will pick out 4 blue class. So automatically, based on the idea of K nearest neighbor, based on the idea of birds of the same feather flock together, you would automatically assign this new data point to belong towards this blue class. So that is how the prediction happens. So the machine learning algorithm will predict the new data point to belong towards the blue class because majority of the neighbors belong to the blue class. All right. So now let's assume we change the number of neighbors to let's say 9 in this case. We're now going to extend it and count the 9 nearest data points close to this new data. So once we count them, we're now going to count the class that has the highest number. All right. So in this case, if we count 9, we'll count 4 here and 4 here. So if we check it, the red class actually has the highest number of classes that are closest to it. So we're going to, based on this K equals to 9, we're going to assign the red class to this new data point. All right. So it's important that you actually pick a very appropriate K value. In this case, you can see that it doesn't make sense to give this new value the red class because it is closest to these 4 blue classes. So this is the idea behind K nearest neighbor. All right, this is it. So if you understand it, you are good to go. So for regression is simple. Classification task. What happens is majority voting. We are going to look at the proportion of the 2 classes or the classes and look at the class that has the majority votes. Majority vote is the number of classes with the highest number of occurrence, and you're going to assign that class to the new data point, right? So why for regression task? what happens is that once you pick the number of k neighbors, you then calculate the average. All right, remember that in continuous variable, continuous in regression, which has continuous variables as dependent variables, the values are what? The values are actually numbers. So you calculate you get the k, right? K nearest neighbor, k near four, maybe four. You get the four nearest neighbor, and you calculate the average. The average from those four nearest neighbor, that value is going to be the value you would give as prediction to this nearest neighbor. All right, that is how you use KNN for classification and regression. As simple as that. All right, as simple as that. So let's see. Let's just look at these steps here. So now, how does KNN work? I've explained it already, so we are still going to go over them one after the other. So you have you just have the steps in your head in case you need to remember exactly how it works. So the first thing that happens is the choice of k. You first have to choose the number of neighbors you want to use. All right. So what does it mean? The number of neighbors is choosing. So k means number of neighbors. So k is a hyperparameter that actually determines how many neighboring points will influence the classification or prediction of a new instance. So they are the one that would actually determine how your prediction would work, or what would how the prediction would happen basically. All right. If you have four, it's four of them that will determine it. If you have five, and so on and so forth. So that is the first step in the KNN algorithm. So the second one here is the distance metric. All right. So the distance metric is something that happens. You don't need to do that yourself, but it's one of the process or one of the steps in KNN. So the distance metric is used to measure the similarity between instances. So you can see here that the distance between each point is measured. So what is used in measuring it is a distance metric. So we have several distance metric. We have Euclidean distance, we have Manhattan distance, we have Minkowski distance. So all these options, they are there for you. And one thing you have to know is that all these options, they are what we call hyperparameters. All right, hyperparameters. So in this case, k is a hyperparameter because you can actually change the value to influence the result of your model. So a hyperparameter is anything that you can change in your model to actually influence the performance or the performance of your model, okay, or the output of your model. That is what a hyperparameter means. So you can see we have different hyperparameters here. All right, so that's what distance metric is used to calculate the distance between instances. Now the next step here is finding your neighbors. So for a given input instance, the algorithm calculates the distance to all the training data set. So once you've selected the number of k and you selected the distance metric, so the next thing is what? Now to calculate the distance. So finding those neighbors. So the way you find those neighbors is by calculating the distance. You look at the closest one. So that calculation is what that calculation is like what is going to determine the selection of the neighbors. All right. So the final thing you have here is a prediction. So the prediction is done based on the on what I explained initially. For classification, the class label is assigned based on majority voting among the key neighbors. All right. For regression, the predicted value is the average of the values of k neighbors. Do you understand? So this is how KNN works. All right. So this is how you can use KNN for classification and regression. So there are some key points you have to consider, or you have to take note of from KNN algorithm. So the first one is lazy learning. I've talked about this already, that KNN is considered a lazy learner because it does not explicitly learn a model during training phase. So as you can see in this, all the steps we did here, nothing was learned. It didn't learn any model. What it just did was just using the nearest neighbor to calculate to give prediction. There was no it didn't map relationship. It didn't capture a pattern. All right, that is basically what the model. It didn't capture that pattern, that relationship between input and output. All right, so it works differently from other algorithms. So it is a lazy learner. So all computations are deferred until prediction. So during training, nothing really happens. All right, nothing really happens during training until all the things that we did here is just what happens, the distance metric and find neighbors. So these things just used to select the neighbors. All right. So during training or during prediction, we then have the class assigned to the new data points. All right. I'm seeing some persons are saying, I don't understand KNN regression. I haven't fully understand. What exactly do you not understand? Okay, so non-para, you can ask a question after the class, so just note your question. So the second one here is non-parametric. All right, so KNN does not make any assumptions about the underlying data distribution. So you can see, remember in linear regression, we talked about some assumptions that needs to be met. All right, KNN doesn't care whether your data is normally distributed or whether it's not normally distributed or whether it is the relationship is linear or not, or it doesn't care about all those things. It does not make any assumption about your data distribution. All right. Okay, but mostly it doesn't actually make assumption about the normality of your data if your data is normally distributed. Okay. So the last one here is the cost of dimensionality. Okay, so there's what we call cost of dimensionality. Cost of dimensionality is a problem in ML, all right, where you have a high dimensional data. So high dimensional data is the same thing as a data that has a lot of features or a lot of independent variables. So one thing in this ML is that you'll be getting to hear a lot of concepts that mean the same thing with other things you've learned. So these things are very easy to confuse somebody. You might be saying, what does this one mean? Not knowing that you already understand it. It's just that this word is another way to what represents what you already know. So dimensionality in machine learning refers to the features. So if you have a lot of features, a lot of independent variables, that means your data set is a high dimensional data set. The dimension is very high. All right. So in this case, the cost of dimensionality means that KNN will perform poorly in a high dimensional space. So what do we mean here? When you have a lot of features, KNN will not perform very well. That's just it. So if your data set has a lot of features, have a lot of independent variables, it is not advised to use KNN. So the reason is given here, because the distance between the points increases, making the concept of closeness less meaningful. All right. So that is basically the key point to know from KNN. So this diagram is just going to show you exactly what happens. So this is the let's say this is a data set you're trying to predict, or you've already mapped out the distribution already, and you have this new data point here, which is what you want to predict. This is you want to make prediction now. All right. So this is before you apply KNN, and at the right hand side is after you've applied KNN. So what happens is that this new data point is classified to be under this green class. All right, so maybe depending on this particular problem, the number of K here was, let's say, 3. So the distance for 3 neighbors were calculated, and it was seen that 2 of them were 2 of the 3 belong to the green class. So automatically the new data point will be assigned to this green class. So birds of the same feather what flocks together. That is the idea behind KNN. So that's it for KNN. It's a very nice algorithm, actually, very, very simple and nice algorithm in ML. And you can see the implementation here. So we are not going to look at this now. Once I'm done with going over the different algorithms for today, we are now going to look at the implementation. So we'll just do everything at once. All right. So let's quickly look at the next one. So we've looked at KNN. So this is the conclusion. In KNN, KNN is a straightforward and effective algorithm for both classification and regression, particularly for small data sets. All right, as you can see here, with well-defined clusters. Its simplicity and ease of implementation makes it a popular choice, although you can struggle with high-dimensional data and large data sets due to computational complexity. So this is just it about KNN. Like, if you have any question, just note it and you can ask it. So we're going to look at SVM. We're going to look at SVM. So please let me know if everyone can still hear me clearly. I think some persons are complaining of that. All right. Okay. So let's just continue. Let's continue. So SVM is another powerful supervised learning algorithm. I'm just hoping that more persons actually not getting enough feedback. But that's fine. That's fine. I just want the momentum to die down. So support vector machines are they are another powerful is actually a very nice algorithm. All right. Although the intuition can be a little bit it might not be as intuitive as the other ones we looked at, but we're going to try to look at that. So SVM can be used as the same with KNN for both classification and what regression. Let's quickly look at it. Support vector machines are powerful supervised learning models used for classification and what regression tasks. So the core idea of SVM is to find the optimal hyperplane. So these are the things you should be noting. All right. So for KNN, KNN was what? KNN was finding the nearest neighbors. All right, using nearest neighbors to determine a class. Right. Why SVM? SVM here is okay. Okay, SVM, the core idea of SVM is to find the optimal hyperplane. So this hyperplane is almost the same thing as is almost similar to the idea of regression line. All right, so just think of it as regression line in linear regression, but they are different for different tasks. So hyperplane is it might be a bit confusing, but hyperplane is just a line that separates two classes. So when we are explaining this algorithm, we try as much as we can to visualize them, because the visualization is the best way to understand something. So imagine you have your data set in a high dimensional space. Let's say you have it in a three-dimensional space, a 3D space. So if you have your data set in a 3D space, that basically means that you have two independent variables and what? Sorry, you have three independent variables, all right, that are classified according to the classes. So you have three independent variables and you actually map them to a three-dimensional space. So what SVM does is that it finds a hyperplane. And a hyperplane is a line, a two-dimensional line. If you have a 3D data set or you're in a 3D dimensional space, the hyperplane will be a two-dimensional plane. So the hyperplane is a lower dimensional space, all right? It's actually a lower dimensional space. If you have a four-dimensional space, your hyperplane will be three-dimensional. If you have a five-dimensional space or data set, your hyperplane will be four-dimensional, and so on and so forth. So that is basically what hyperplane is. So the work of hyperplane here is basically to separate your data points of the different classes. Remember, we are trying to classify our data here. So you are trying to learn or get a hyperplane that perfectly separates your classes rather, all right, in that particular feature space. So all these things are actually sounding quite confusing. Like I can relate, right? Especially if you have not heard of this before, and if you are not familiar with some of these concepts. So if you are familiar with some of these, like let's say geometry and all of those things, this will not be an issue for you. All right. So, but let's try as much as we can to give you an intuition. So that's why I don't want to go into the details so as not to confuse you, but to just help you understand at the surface level, so you have a good enough knowledge to implement this in SVM. And when you get very comfortable with it, you can move ahead to actually get and learn more details about those algorithms, right? So I'm going to start all over again for SVM, so we follow along. Okay, you can keep your questions when we are done. You'd ask. So support vector machines, we're going to break it down now. So support vector machines are powerful supervised machine learning models that can be used for classification and regression tasks. Now, the core idea of SVM is to find the optimal hyperplane. I think the problem now is hyperplane. So hyperplane is what, as I said, is a suboptimal dimension. Let me come again. Hyperplane is a suboptimal dimension that is used to separate your classes. So that is basically what SVM is trying to do. It's trying to find that suboptimal plane. Suboptimal basically mean a lower dimension than the dimension of your feature space. Okay, so it is like also what we call decision boundary. So you can also call hyperplane a decision boundary. It can be a line, all right. It can be a plane, a 2D plane. It can be a 3D plane if your feature space is 4D and all of that. So just think of it like that. If your feature space is in a higher dimension, your hyperplane is one dimension lower than it. Okay? If you're in a 2D space, let's say you are working with two features, let's say height and width, right? The hyperplane is is simply a line, because a line is a one-dimensional. A line is one-dimensional. So if your feature space, if your data set just have two features, that means your hyperplane is a line. If you have three features, let's say height, width, and age, the hyperplane is a flat surface or a plane. So it's going to be a two-dimensional plane, right? So in higher dimensions, in dimension higher than 3D, if you have more than three features, the hyperplane actually becomes very difficult or impossible to visualize, right? So you remember that we can actually visualize higher than 3 dimensions, but mathematically, you just have to understand that it's just a boundary that separates your data. Okay, it's just a boundary that separates your data. So how does your support vector machine find that perfect hyperplane? Remember, in linear regression, your linear regression model has to find a line that minimizes the what sums of square error, but it doesn't just draw any line. It has to get that particular line because the possibility, the lines that you can actually get, they are numerous. You can get thousands of lines, but you need just one line that perfectly captures that relationship, that minimizes the sum of square error between basically reduces the sum of square error. The same thing comes here. How does SVM select the hyperplane? So SVM is not doing the same thing. It's not calculating error and all of that the same way linear regression calculates error. So there's another concept that you now need to understand in SVM, which is what support vector and what margin. All right. So we've looked at hyperplane here. We're going to look at now support vectors and what margin. So now, support vectors, what exactly are support vectors? That is like literally the name of the algorithm. Support vectors. Vectors in this case, I don't know why in this field, a lot of things, a particular concept has different word representation. So a vector in this case is the same thing as what? A point, a data point. Okay? So all these things you are seeing here, you can see a lot of data points here. Let me zoom out so you see very well. You can see a lot of data points. So all these data points, they are called vectors. Just in SVM, they are referred to as vectors. Just have that at the back of your mind. So a support vector is they are those data points or vectors that are at the edge of each class. Okay, they are the one at the edge of each class. So if you look at the two classes, for example, you look at this green class and you look at this red class, you see that the support vectors here are what? This one here for the red class, we have this one for the green class, and we can also include this one here for the green class as well. But what we are looking at, focus on, are just the ones that are at the edge of the two classes. So once you get these support vectors, right, you now draw a line basically. SVM gets the support vector and draws a line. So this support vector is actually what we determine where the hyperplane would be positioned. Now we are talking about how does SVM determine the particular hyperplane or the position of the hyperplane, because this hyperplane that we have in here, it can be here, it can be here, it can be like this, it can be so. There are different possibilities, different ways the hyperplane can be positioned, but we need to get the perfect position for the hyperplane. That is what support vector machine is trying to achieve. So it tries to achieve that by looking at support vectors. So the support vectors are this, what I just explained now. So it gets those values, all right, as you can see here. Support vectors are what? They are data points that are closest to the hyperplane. Okay? They are closest to the hyperplane. They play a crucial role in defining the position and orientation of the hyperplane. That is basically what a support vector is. Now let's look at margin. Now the margin is what? The distance. Let's zoom in. Margin is the distance between the hyperplane and the closest data point, all right, which is basically the support vector. So the margin in this case is what? See the margin, as you can see here, this is the margin from here to here, right? This is the margin between the hyperplane and the closest data point or the support vector for this class, and the margin for this one is from here to here. So what does the margin do? So the margin is the distance between the hyperplane and the closest data point from each class. SVM now aims to maximize this margin to improve the model's robustness. So What SVM is trying to do is to try to maximize, get the maximum distance or the maximum value for the margin. So getting the maximum value for the margin means that it's trying to get the best separation from the two classes. All right, it's trying to get this best separation. So the higher the margin, the better the separation of the classes. The closer the margin, the the worse the model, the worse separation you are going to get. You're going to get a very bad separation if the margin is actually close. All right, but if the margin is if the distance, if the margin is high, you're going to get a better separation. That's basically it. You get a bad separation if you have a low margin, and you get a very good separation if you have a high margin. So what SVM tries to do is to try to get try to maximize the margin. Maximizing in this case is to get the highest margin possible. So all these things that I just explained now, these are the things that happens during training. So SVM calculates all these things, and then after it has determined them, it will now draw the hyperplane. So once it gets that perfect hyperplane, right, it's now going to be used for prediction. So when you get a new data point, and that data point falls in this particular place, all right, in this anywhere above or below the margin, you can now know the class that that new data point will belong to. That is how the prediction happens. Don't allow yourself to don't allow yourself, don't worry so much about understanding the nitty-gritties of this SVM that I just explained. I'm just trying to build an intuition, so you just have the overall understanding, so you can take your time later on to understand it, right? Most of this machine learning algorithm is not something you understand. It's not a one-shot something. It's not something you understand immediately, right? I myself, I actually didn't understand this at the go, so I had to take my time to understand some things and all of that. So I'm just trying to build a foundation for you here. So as time goes on, you definitely understand it. There's some concepts that you might not understand, like for a while. You keep trying to just but the main thing is that just try to keep trying to understand those fundamental concepts. In this case, like hyperplane, support vectors, margin, and all of that. So those are the things you need to know when it comes to SVM. Now, there is another concept here in SVM, which is called kernel trick. So this is very important because SVM can also be used for non-linear data. Non-linear data. In this case now, you can see that this is actually linear data. All right, this is actually a linear data. Can someone, okay, let me not just go there. The reason why this is this is a linear classification, right? This is a linear classification. Can someone tell me why this is a linear classification? Let's start to interact now, right? This is not something I've said before, right? But based on what you're seeing here and based on your knowledge of linear, what linear is, can someone tell me why this is a linear classification? Thank you. Everybody just say straight line. Straight line, straight line, straight line. Only Adebayo said the hyperplane is linear. Okay. All right. So yeah, I think you all are saying the same thing, but you're just trying um to say it in a very short way. Yeah, I get you. I get your answer. So basically why this is a linear classification is because the classes are linearly separable. That is the thing. They are linearly separable, basically meaning that they can be separated with a straight line. All right. They can be separated what? With a straight line. So if you have a data set or a data set here that the classes cannot be separated with a straight line, that is a non-linear classification. So SVM can actually handle non-linear classification. Okay, let me show you an image of what we mean by non-linear classification. Look at this image by your left hand now. All right, look at it. Can it be separated by a straight line? These are two classes. This blue class is one class, while this red class is another class. Is it possible for these two classes now, for this particular data set to be separated with a straight line? No. All right. This is an example of what? Non-linear classification. This is an example of what? Non-linear classification. So SVM provides techniques that can allow it to work with non-linear data. And what it does is that it projects, if you have your data in two-dimensional space, it projects that data into what? Three-dimensional space. So as you can see it here, you can see this is the projection happening now. It projects it into a three. I'll answer your question, Jafet. It projects into a three-dimensional space, and it then used a linear hyperplane to separate it. All right. So you can see in the middle here, this is a three-dimensional feature space. All right. So you can see that this red data is the same red data that we have here, but a transformation occurred, right, in which the red classes were projected into, the two classes basically were projected into a higher dimensional space, allowing SVM to now use a hyperplane to separate it. Because you can't actually use a hyperplane to separate this, it won't work. So the only way to do that is to project it into a higher dimensional space and then separate it with a hyperplane. So once you do that and you visualize it with your two-dimensional, you see that the separation will be like a circle here. But in reality, what happened was this, right? The separation was performed by a linear hyperplane. By hyperplane is always a plane, a line. Hyperplane is not a curve or anything, it's a line, all right, or a plane or a straight flat surface or something. That is what hyperplane is. So for you to be able to use hyperplane for non-linear data, that non-linear feature space have to be projected into a higher dimensional space where the hyperplane can appropriately or adequately separate the data set. Are we understanding? Hope we are following with this, and it is very easy to grasp. Hope we are following. All right. That's good. Okay, Jafet, you said, does the algorithm for SVM automatically find the support vectors? Yes, that is part of the training. That is part of what the algorithm does. All right. It finds the support vector itself, and it then gets the hyperplane and then look for. So those things I explained. Everything happened during training, right? That is what happens during training in SVM. Okay. So you can see another example here. You can see we have two different kinds of classification. We have a linearly separable classification problem, and we have a non-linearly separable classification. We can actually use a line to separate these two classes. So what do we have to do here? Based on what I have said now, what happens in this case, in this particular case, I just said it like a few seconds ago, a few minutes ago. Okay. I need more persons to answer. I want more intervention. Okay. All right. Okay. So that's fine. That's fine. I just wanted more participation. So use KNN to predict the value, right? To use hyperline to separate them. SVM has to project it to a higher dimension. Thank you, patience. Olabode, you take it to a higher dimension. Thank you. Projection, convert to a higher plane on 3D. Change the dimension to 3D higher dimension. We need to use the hyperplane. So yeah, those that said projecting to a higher dimension, you are correct. That's it. That's basically what happens here, or that is basically what will happen in this case. This data set will be projected to a higher dimension, in which case it's going to be a three-dimensional data, and then a 2D hyperplane will be used to separate it. All right, so the separation can happen like this. You have to project it first, then use your hyperplane to separate it. As simple as that, right? As simple as that. So now let's quickly look at some other things quickly. So what happens, or the function that is used in converting this hyperplane is what we call a kernel, right? Kernel is another concept in SVM where we actually so we can see SVM can handle non-linear classification by applying a kernel function. So a kernel function, zoom in, applying a kernel function which maps the input features into a higher dimensional space where a linear separator can be found. Like, as I'm explaining this, I'm even understanding it the more. So it means you should also be understanding it, because this SVM is not very intuitive. All right, so I'm trying as much as I can to break it down. So the kernel is what transforms the your data from a lower dimension or to a higher dimension, where a linear separation via hyperplane can be used to separate the classes. So once you separate the classes, then you can now, that you've created your model already. So we have different kernel here. We have linear kernel, right? This is I think this one for just linear classification. We have polynomial kernel. We have radial basis function kernel. We have sigma kernel. See, don't rack your brain about what all these things mean. Like, even me, I don't even know what radial basis function kernel is. Like, I don't know in details what it is. Why it's a kernel for non-linear classification. So one thing in machine learning is that you don't need to know every single details unless you are writing a research paper or you are into research, ML research, and you need to understand the details of all these things. Because at the backbone of all this, there are mathematical equation and all of those things that you don't like. Most of us don't like. All right. So but if you love it, then it's very nice. You can as well explore them. So that doesn't mean you shouldn't be curious. So that doesn't mean you shouldn't want to learn more about this thing. By all means, please do. But I'm just trying to let you know that as I'm explaining these things now, don't start trying to ask me these questions that, okay, what does radial basis function, polynomial, and all of this. So that's just by the way, all right? So the ability of SVM to handle non-linear classification is done by kernel trick. So that's what we call it in SVM. Kernel trick is the concept that we use when SVM wants to like actually classify non-linear data. So that's it for the concept in SVM. So I actually focused more on the classification, right? The regression SVM is an adaptation of it, right? Just going to briefly look at it. So how does SVM work? So we have three stages. We have the training phase. So in the training phase, the SVM constructs a hyperplane or what set of hyperplanes in a high dimensional space. So in a high dimensional space, most of the time your data set is like 13 dimension, 14 dimension, depending on the number of pictures. Your data set can be 20 dimensions, sometimes it can be 50 dimensions. So you can actually try to imagine how the hyperplane would be because you can't visualize more than 3 dimensions. So everything happens mathematically. So after it has constructed set of hyperplane in a high dimensional space, it then selects the hyperplane that maximizes the margin between the different classes. So are you seeing how everything is coming together now? The aim is what? To get a hyperplane that maximizes the distance between the two classes. Margin is also the same thing as distance. The same concept applies in linear regression, where your linear regression model is trying to select that line that minimizes the error. All right. In this SVM, it is trying to select the hyperplane that maximizes the distance between the two classes. All right. That is what happens in training. Then after that, the prediction, new data points are then classified based on which side of the hyperplane therefore. So the prediction is just very simple. If your new data set falls in this part of the hyperplane, then it will be the red class. If it falls on the other side, it will be the green class, as simple as that. That is just how SVM for classification works. Okay, so SVM for regression, I'm not going to do much on it, but what it does is that it uses it. It actually tries to create a tube. Let's just leave that. You know what? I'm just going to let's quickly finish the remaining ones we have for today. That one can be quite confusing, but if we have enough time, so we're going to look at that. If not, then I would send a video or look at it in tomorrow's class. But trust me, it's just a side knowledge. All right. Once you understand the concept of SVM and all of that, you can just pick it up and learn as you go and understand it better. So, but in summary, what SVM regression is trying to do, it has different concepts as well, right? It's what we call epsilon. So it uses what we call epsilon sensitive tube. So the tube is like the line in linear regression. So it tries to create a tube around your data, right? A tube that is very narrow, all right, but at the same time captures most of your data. So that tube is now going to be what will be used in predicting. So I don't want to go into details on how the tube is created, but just keep that at the back of your mind for now, all right? So the support vector in the case of regression are the vectors that are outside the tube. So they are those vectors that determine how the tube would be created or the position of the tube. So in the case of regression, the support vectors are outside of the tube, and the values inside the tube are the remaining data points. And the tube tries as much as it can to capture as many data points as possible, and at the same time minimizing the width of the tube. It tries to make the tube as narrow as possible while at the same time capturing as many data points. So once you can get that particular tube, that's the model. So once you get the new data set, you can now map it to the position in the model in the tube, just like linear regression, and trace it, and the prediction can happen. So that's the core idea. That's a very superficial explanation of regression in SVM. All right, so let's quickly look at, we have the last model here, which is decision trees. So we're going to look at how to implement all of this. Don't worry. We're going to look at how we can implement KNN, regression and classifier, KEM, SVM, classifier and regression, and also decision tree, classifier and regression once I'm done explaining. So we have the last one for today, which is decision tree algorithm. Decision tree algorithm. So now this decision tree algorithm is actually a very intuitive algorithm, right? It's like a tree, an upside down tree, where the roots is up and the leaves are down. So imagine a tree and you carry the roots and you invert it, right? The root is now up and what the leaves are now down where the root is supposed to be. That is what this algorithm looks like. So if I zoom out here, you can see the diagram. So all these things you have at the end, they are the leaf. They will call them the leaf node, and the node we have at the beginning is called the decision node or the root node. So you can see this looks like an inverted tree that has the roots at the bottom, at the top right, and the leaves at the bottom. So we're quickly going to look at that and move ahead with the implementation. So decision trees are a type of supervised learning algorithm. So everything I've been talking about today, they're actually supervised learning algorithm. All right. And it can be used for both classification and what regression task. Okay. So I thought said KNN can be used for both classification and regression. SVM can be used for both classification and regression. Decision tree can also be used for both classification and regression. And the algorithm for classification and regression, for each of these algorithms, the way it works is different though. You understand? So I'll actually explain the way the prediction for the classification is in KNN and also the regression. The same thing for SVM, the idea behind the classification for SVM and the idea briefly on the regression as well. So the same thing will happen here. I'm going to actually dwell most on the classification aspect of decision tree because it is used mostly for classification tasks. All right. So decision tree is like the foundation of the algorithms we're going to be looking at tomorrow. We're going to be looking at some algorithms tomorrow, like random forest. All right. So these are actually based on decision tree algorithm. So are we enjoying the class so far? I can see some persons. Okay, yeah, great. So what are decision trees? Decision trees are a type of supervised learning algorithm used for classification and regression tasks. They work by splitting the data sets into subsets based on the value of the what input features. I'm going to say it again. Decision tree work by splitting the data set into paper funny. Say enjoyment gidigba. Enjoyment galore. Okay. All right. So they work by splitting the data set into subsets based on the value of the input features. So it creates a tree-like model for of decision. Each internal node represents a feature or attribute. Each branch represents a decision rule. Right. So what do we mean by that? So there are different concepts to know. I've told us what this is. This is the root node. Okay. This is another node that is based on this particular one here. And then we have the final node in the decision tree is what we call the leaf node. So that is where we come to the end of it. So what happens exactly? What is happening? Like how does the data come into play in this decision tree? So let's look at the different concepts here, one after the other. So we have hope everyone is still following me. Like, let me be sure. Okay. All right. So we have the root node. So the root node is the topmost node in a decision tree that represents the entire data set. So you've actually not split. What you are doing in this in decision tree is actually splitting the data sets based on what certain features. All right, splitting the data set what based on certain features. So what the root node is the initial split before you split your data set. And what the criteria you use in splitting are actually features. You use different features to split your data set. Okay, so I'm going to use an example to illustrate this, right? So let me just quickly go over this concept. We're going to use an example to that you would actually understand, use to understand it. So we have decision nodes. All right, so decision nodes, they represent the features value that leads to decision to further split the decision. So these are actually features that we'll be using in making the split, right? So each node that is being split in decision tree is called a decision node. Even the root node is called a decision node as well, but it's also the root node because it's the initial split that we are making. So each subsequent split is going to be called the decision node, right? So the other thing we have here is the leaf node. So this leaf node represents the final class label or outcome of the decision process. So remember, we're trying to classify a data into different categories. So the leaf node is going to have the classes that we are trying to the categories that we are trying to classify basically. So in this case, these leaf nodes here, let's say we are trying to differentiate between, let's say, what example am I going to use? So let's say you're trying to classify a picture, whether it is a dog or what, or a cat, or not necessarily a picture. You're trying to classify, you're trying to use a data set to classify whether those particular features correspond to a dog or a cat. So what you're going to have in this leaf node here are going to be either dog here or cat, dog, cat, dog. So those are the things that will be in leaf node, the classes. If you are trying to classify spam, whether this email is spam or not, the leaf node is going to have what? Spam or not spam, spam or not spam. So everything leading up to this spam and not spam is going to determine how the prediction will be carried out, right? So let me just use an example because this might be getting confusing. So first of all, let's assume we're trying to classify animals into two categories, dog and cat. And we have, let's just use, we have two features in this case. We have what? Size, sound. Okay, we have size and sound. And let's say we also have clause, like if it has clause or not. Or let's just use size and sound for simplicity's sake. So we have size feature. So for size feature, we have, let's say, three values. We have big size, medium size, or small size. Okay. For sound feature, we have bark or meow. That is for the cat sound and the dog sound. So we have these two values for that particular feature. So we want to use these features to classify whether this is a cat or a dog. So using decision tree, what we are going to do is that we're going to start with the root node here. Right, this root node, this decision node. We're going to start with the question. So selecting the feature is now one of the things decision tree will do. So which feature are we going to select now that will classify the classes, that is dog and cat, perfectly? It's going to start with the first one, which is what sound. All right, which is sound, a bit size rather, which is size. So in the size feature, we have three. Let's say we have large and small. Okay, so it splits the data set based on these two values. So we have now in this node here large, and we have in this node here small. So if we check all the label of our data set, which is dog and cat, we check it here under large and we check it here under small. We will now check the proportion of the cat label to the dog label and check the proportion of the cat label here to the dog label. Now, there's what we call entropy. Entropy is the metric that the decision tree used to select the feature. So depending on the purity of this classification here, it's going to decide whether to go with this feature. So let's assume in this case, we split into large and small, right? So in this large node, decision node, we have, let's say, 30 data points here. And in this place, we have 30 data, or let's say we have 20 data points, right? So let's say the total number of our observation is 50. When we split it, we have 30 data points here, and we have 20 data points here. So we now looked at the different data points in this large, and we saw that out of the 30 here, 25 of them are actually dog, all right, and 5 of them are what, cats. We come to this small value here, and we see that out of the 20, 15 of them are what, cats, and what 5 of them are dog. So we can see that there's actually a good the proportion is actually pointing to a higher purity. All right. So the proportion is not very random. So we will now start considering the entropy, calculating the entropy for each of these splits. And the entropy value is going to determine which feature. So we did this for the size feature. So this same process I just explained now will be done for the sound feature. So the sound feature is what? Bark and meow, which are the different sound, the different animals, which are dog and cat make. So once we split it to bark here, let's say this place is bark and this place is meow. And then for bark, we have, let's say, 30 features as well. And out of those 30 features, 29 of them are what? Dogs. All right. And when we come to this place, meow, we have 20 and 18 of them are what? Let's say cats. So this particular split has a very high purity. The entropy will be calculated, and what the entropy will now be compared with the entropy of the size split, right? You know, we splitted with each feature. That is what happens. The split at the decision node will be carried out for each feature. So the selection will be done based on the entropy of that particular split. So let's assume at the end of this split, we checked all the features, and the feature with the highest entropy was what? The sound feature. Decision tree will now select that as the root node and use that as the initial split. All right, we'll use that as the initial split. So once we split this, we are now going to perform the same thing here. We'll now consider this like the root node that we have here. So in this place, we have 30 features and 30 data points, all right? So we'll now select another feature that we'll now use in splitting again. We've already used sound to split, then we can now use size to split. So this is basically what happens in the decision tree. It's a recursive algorithm, all right? It's a recursive algorithm. It can be very complex to understand initially, but this is what happens, especially when you have a lot of features. It goes through each of those features and performs splits on the root node and compares the entropy of each split, and the entropy will determine which split will be the initial split. And the same thing happens over and over again till we get to a point where we cannot actually split again. All right, where we cannot actually split again, and then we have our leaf node, and we can now use this particular model. So the particular split that we have with the best entropy is going to be our model. So when we have a new data point, all right, we have a new data point with a value for size and a value for sound. We're not going to come here and ask, okay, what is the size of the particular animal? Okay, say it's large. You will come here. All right. So what is the size is large right now? What is the sound? The sound is what bag. Okay, we'll now come here. So this place is not going to be dog. So we're not going to predict that new data point to belong to the dog class. All right. If it is large and it barks, then it's dog. If it is large and it meow, then it's cat. So if you come here, this place is small, right? If it is small, right, and if it is small and it's, let's say, it barks, then you come here. So this is dependent on the number of features that we have. So this is just a rough diagram to explain this. So depending on your feature, you have a different kind of diagram, a different kind of decision tree diagram. If you have a lot of features, you have a more lengthy decision tree with a lot of branches and a lot of leaf nodes and decision nodes and all of that. All right, so this is decision tree, right? This is what happens when you use decision tree. I will understand if at this point you are overwhelmed. Very, very understandable. Don't fret at all. It's actually very normal. Okay, if you understand it, that's fine. But if you don't, please just don't beat yourself up. Just make sure that at the end of this class, you go over this video again. I'll still send materials. All right, I'll particularly send video materials. I'll particularly send video materials for these algorithms that we've talked about today, so you can further look at them and particularly understand them visually, because that is the best way to understand it. So I'll look for materials, video materials that explains these things using visuals. All right, so just expect them at the end of this class, so you get a better intuition of these algorithms. So that's it for decision tree classifier. The same idea also happens for regression. But before we look at that, let's quickly look at the key concepts here. So the topmost node in the decision tree represents the entire data set, which is then split into two or more homogeneous sets, which I explained. Then decision nodes, these nodes represent the feature values that leads to a decision to split the data into subsets. We have leaf nodes. These nodes represent the final class, labels, or outcome of the decision process. We have splitting. Splitting is the process of dividing a node into two or more subnodes based on a certain feature value, right? If you have three categories in your feature, you split it into three branches, all right? So I use two for simplicity's sake, all right? So you have pruning. Okay, pruning, this process referred to removing the section of the tree that provide little power to classify instances. So in the case where I talked about purity and entropy, those ones that have high entropy, in our chemistry, we talked about entropy. Entropy, can someone just remind us what entropy is? Let me see if at least we understand that concept first of all. Okay. Let me just entropy is a general word, right? It refers to exactly. Thank you. Entropy is like the randomness or disorderliness. When there is something has high entropy, that means there's a high disorder. All right. The randomness is very high. There's no order. There's no arrangement. You can actually see a pattern in it. All right. That's what entropy is. So when you are creating or splitting a decision tree at a node, if that node has high entropy, that means the split it has low purity. All right, and it's not a good split. Let me just put it that way. If it has high entropy, it's not a good split. If it has low entropy, it's a good split. So it's like a metric to determine how good a split is using decision trees. All right, but entropy is actually not the only measure of purity. We have Gini impurity, we have entropy, and we have information gain. All these things, they actually do the same thing. All right, they do the same thing, but different algorithms, different methods, just like Euclidean distance, Manhattan distance, and the other ones that we saw in KNN. So these things are hyperparameters. They are the things that you can actually change to improve your model or change the way it behaves. Okay, so impurity measures is another thing in decision trees. It's a criteria used to decide how to split the data at each node. Okay, so that is where you determine your splits. We have Gini impurity, we have entropy, and we have information gain. Okay, so these are the things that you have to look at, the concept you have to look at in decision trees. So how does decision tree work? I've already explained this, so I'm just going to go over this quickly. So first of all, during the training phase, you will start at the root node. So all these things happen when you are training it. You don't need to do anything at all. All this information I'm just giving you just for you to understand it. That's why you're a scientist, data scientist. You need to understand what's happening in case there's an error somewhere, so you know where to trace it to. All right. So how does training work? I explained already. First of all, you start at the root node, and select the best feature using a measure like Gini impurity or entropy. See, this is what I have explained. It will look at all the features and select the feature with the best entropy, the best the lowest entropy, basically, right? You are looking for the feature with the best splits. That is it. That way you're trying the best split. That is the best purity. When you check the proportion of the two classes, you see that the proportion one is not just random. It's not 50-50. It's like 90-10, 80-20, 95-5, which is a very high purity, something like that. So you select that feature, and then you split your data based on that best feature. So once you do that, you now repeat the same process on the remaining features that you have until you reach a stopping criteria. So there are different stopping criteria in decision tree. We have maximum depth. So you can actually set the maximum depth of your decision tree. You can say once it reaches five nodes, you stop splitting. Okay. So these are the things that you're going to see in Scikit-Learn. There are hyperparameters that you can set. So this is what happens in the training phase, right? These different steps. Once you've done that, you've created your model. So that model cannot be used in prediction. So what happens during prediction? So in prediction, you traverse the tree from root node to the leaf node, making a decision. So a decision will be made based on the features of your new data set. All right, it goes from the root node and follows a particular direction based on the features that new data set has. And wherever it lands, right, the value of the wherever it lands in the leaf node is going to be the class that will be assigned to it. All right, so that is just what happens during prediction. So that's it for decision tree classifier. So the same thing happens in regression, decision tree regression. It's just that now you're working with continuous value. So you're going to have to, instead of splitting into different categories, you now split based on a range of value, maybe from 0 to 5, from 5 to 6. So these things happens themselves. You don't actually specify all these things when you're using the decision tree. So you just do model.fit and then put your data set, and you make sure you've already pre-processed your data set already to be able to so that you can use it with the machine learning algorithm. So you don't need to stress yourself on all these details that I've just explained now. They are the things that happen automatically when the algorithm is running, when you are training your data set. Okay, I just need to explain this so you understand what is happening. All right. So let's just continue. So that's it for decision trees. So we've looked at three algorithms now. I think these ones are actually a little bit more complex than logistic regression and linear regression, right? So we'll look at how we can implement it in Scikit-Learn. So that's going to be actually very quick and going to be the last phase of this class. So let's move on to Scikit-Learn. How do we implement, how do we use all these algorithms that we've talked about in Scikit-Learn? So as usual, let's start with KNN. Importing KNN classifier and regressor. So to import KNN, you would have to say from sklearn dot kn. Sorry, I think neighbors. Yeah, neighbors. Neighbors. Import KNN classifier and also KNN regressor. Regressor. Okay, I think this should have you. I don't know how to spell neighbors again. Here is G, okay, H. So I think I have to see, I think it's K neighbors classifier and K neighbors regressor. So this is how you import your KNN classifier and KNN regressor from Scikit-Learn. So you say from Scikit-Learn.neighbors, import K neighbors classifier and K neighbor regressor. So let's quickly import our data set as well that we're going to be using. So importing data sets. So from Scikit-Learn data set, import, okay, from Scikit-Learn, yeah, data set imports, I think include diabetes, right? Don't know what's wrong with this. So this is going to be for our classifier. This one is for classification. Then we're going to import another one for regression. Yeah, so I'll say Scikit-Learn.data sets, import, I think load I think California housing is one data set here. Screen is moving. Please, can someone else confirm if that's true? Please, can someone else confirm if that is true for everyone? All right. Okay. So I'm going to see if we can get California housing. This will be for regression task. So we've gotten our data. Let's just load our data set. Loading our data set. We're going to say X classifier. Oh no, let's just say X and say X1. All right, this is going to be for our classification. We need to say load diabetes. All right, and we'll come and say Y1 first load diabetes. I think this diabetes, am I sure it is sorry, load diabetes, sorry, data. I'll come and say X1 is equals to data dot data and say Y1 equals to data dot target. So let me quickly see if oh, okay. So this is just, let's make this breast cancer. Breast cancer, okay, because we need that for classification. So yeah, we want to have a classification data for the classifiers and also this one is for classification. So we're going to do for loading regression data sets. So I'll come here and say data 2, not data 1. Okay. So it's more conflicts. I'll say fetch California housing. Right. Fetch California housing x2 equals to data 2 plus data. Say y2 equals to our data 2 the what target. So yeah, we've loaded our data set, and now what's the next thing? So can someone tell me the next thing? What are we going to do next now? We want to implement the models that we've looked at. So what X1 and Y2 should now use data 1. What do you mean by that, people? Can someone tell me the next thing after this? We've loaded our data. So what do we do next? What do we do next? Exactly. So we're going to split our data. X1 and Y2 should now use data 1. X1 and Y2. No. These are two different data sets. This is the first data set is for classification task, while the second data set is for regression task. All right. What I'm trying to do, I'm trying to show us how we can use both the classifier and the regression part of our algorithm. So we need the classification data set and also the regression data set. So we are doing it simultaneously. Okay. So next thing here is to split our data set. Okay. Data, thank you. I think I get this now. You changed the. Okay. I think I get your point now. Thank you. Thank you for that. All right. So now we'll split our data and then we'll do the splitting for each of the data sets. So for X1 and XY1, we're going to do X train 1 and X Y train 1 and say x test 1 and y test 1. So we have to import this. So let me just copy this and put in the same place as this. All right. So I'll say from sklearn dot model selection import train what test split function. So come here and say train test split. Right. So I'll come and say I'm trying to split x1 and what y1, and test size will be what? Test size will be, let's make it 20%, and random state should be 22. So this is going to be for splitting classification sets. So we're going to just copy this so we can be very fast. Data set, come here and say S2 2 2 2. Then I'll come here and say x2 y2. So I'm doing this because I'm doing the regression and classification simultaneously. All right, so we don't waste time. So I run this, and then after splitting, what next? So what comes next after splitting? So I'm following your lead here. So let's have it. What do we do now? What do we do now? Exactly. So we go straight towards training. So now we're going to look at how we can use each model, each algorithm to train our data. So we've looked at all of them. So what I'm going to do, I'm actually going to just import everything. Importing the models, right? So I'll come, I want to import decision tree. I'll say from sklearn, but let's import SVM. I think SVM. All right, import SV from SVC. All right, signifier SVC SVR. All right, so this is how we import SVM, SVC, and SVR. So we import decision trees, sklearn dot tree, then tree, right? Tree, import decision tree classifier and decision tree regression. So yeah, we've imported everything now. So all the things all the algorithms we looked at today, this is how we can import them from sklearn. Okay. So now we'll now go and instantiate everything for model training. Okay, let's quickly look at that now. Training model with, let's start with KNN. Let's say classification model with KNN. So how do we do that? We just have to instantiate. We have to instantiate the model KNN classifier. All right. That is let's say K classifier equals to what? K nearest neighbor. Right. So this is how we instantiate it, and then we come and say Let me just run everything at the same time. Let's see because of time. So let me just go one by one for you to not get confused. So now inside this bracket here, all those hyperparameters I talk about, we can place them here. Remember in logistic regression and linear regression, we looked at them. For k-nearest neighbor, we have n neighbors, which by default equals to what, 5. Okay, so this is a hyperparameter. We can change it if we want. We have the metric, the distance metric here, and by default is Minkowski. We have the Euclidean distance also, and we have the let me scroll down. We have the Manhattan distance. So you can see it here, Euclidean distance, and we also have I think the Manhattan distance should be there as well. So yeah, that is it for it. So if you want to change it, you can come and say n what neighbors. You can make it 3. Or I want to make it use 3 neighbors to determine which class our this thing will belong to. So I'll come here and say I've already created my model. I'll just come and say k classifier dot fit. Come and see which one is classifier again. Is it the S first one? Okay, that is x1, x1, y1. I'll come and say S train 1 and what? Y train 1. So as simple as we've done before. So every other thing from this point is basically the same thing we did in the previous class. So if I run this, to actually run without what error am I getting now? Found input values because the number of samples. Oh, let me be sure I split this thing well. Yeah. So, oh, sorry, this should be x test 1 y train 1. Nobody even corrected me here. So this is how we split here, so we don't get mismatched variable type. Or unknown level continue to run plus for just plus. Okay, let me print them out to see my values. What? Actually, okay. Y1 was this is breast cancer. Breast cancer should be let me see my Y1. Yeah. So let me load it again. Right, training. Okay. I see. I can see it here. So it's just one of the headache you get when trying to do both classification and regression problem at the same time. So you should get this. All right. Okay, so I think it should work now. So now you've created your model. You can see nothing happened. I told you that KNN is a lazy learner. It doesn't really learn anything during training. So you just have to come here and you can now use it for prediction. All right. So today we are not actually evaluating our model. So we are not going to be dwelling on that. I'm just trying to show you how you can train with different models that we've looked at today. So I've already showed us how you can evaluate classification task and what regression task. So the concept we did, the concept that or what we looked at in the previous class in evaluation is the same thing applies here, right? So if you want to get the accuracy here, you can come and say k what was k classifier, all right, say dot predict, and you come and say y x what test 1, and you assign it to what y read. You run it, will give you a value. So you can come and now say accuracy, or you can just say classification report, and you put y what test one and y read. So you have to import classification report. You have to import it here, all right? So dot model, I think dot metrics, right? So you say import classification report. So come back here and do this. So you'll just print it out. You will see. So you can see the output here. You can see the position, recall, F1 score, everything, your accuracy, 92%. So you can just use the same evaluation that we've done previously to evaluate your model. So whether you're using KNN classifier or you are using decision tree, or you are using SVM. But let's try to create a function that will just take in a classifier and give us output. So I'll say model classification. So to take the model here. So what will happen is to be so what is it going to take here? So model dot fit. All right, come and say x train. I will take my data as well. Right, x train and what y train, x test and what y test. I'm just trying to create a function that would do everything at the same time. So I'll come and say model.fit x train y train, then model.predict x test y test. So I'll assign this to y predict. Okay. So once I come here, I can just say classification report equals to y test what. Sorry, this one should be only x test here, and what y read. So I come and say reports, and then come and say print report. Okay, so you can create this function, can just use it for any of our model here. So I'll come and see for decision tree classifier, I can come and say decision tree I'll just say tree as a decision tree classifier. All right. For SVM, I'll come and say SVC, which is SVC classifier. I'll say SVC. So for KNN, we already have our KNN classifier. So I can now come here and say model classif. All right. So for my model, I can put tree first. All right, and put my x train 1, y train 1, 1, x test 1, and y test 1. So if I run this, it should give us a value. So if I change this model to any of our classifier model here, you'll see it will be giving me classification model based on the model that I put here. So if I put K classifier, you see it give me a different thing. So this is just a way of showing you that you can use different algorithms to on your data sets and look at the one that have a very good performance. So today we are not actually comparing models. Today we are not trying to see the model that perform best. We are going to do that in the next week, subsequent classes, where we are going to actually looking at comparing models with the different metrics that we've used, and we're also going to be introducing ROC AUC curve, which we didn't look at in the last class. So this comparison will be after we've looked at all the algorithms and how we can use them. So it's actually going to get interesting from here. So just brace up. We've actually we are now starting fully. We are now starting machine learning fully. So yeah, you can put whatever it is you want to like. So you can create your own regression model yourself. I would urge you to do that. This is not an assignment. This is just for you to practice as well. Create a regression model and do the same thing here. And you can import the regression model for KNN, SVM, and SVC, and look at them on the different data set and you see how they fit. So if I come here and I say, okay, let me just use this. I'm just looking at time. Function for explication. So you know what? I'm going to leave it here. I'll make this notebook available to you on Google Classroom today. So this is not an assignment, it's just a task for you to do. It won't be graded. Just complete the regression part of this. All right. Complete the regression part of it. I've already explained everything. I helped you build intuition on these different algorithms, right? So and also showed you how to import them from Scikit-Learn. So you can see training model is the simplest part of machine learning. The training part is the simplest part. The part you actually stress yourself a little is evaluation, understanding how the model work, pre-processing as well. So pre-processing is a very key point or key step in machine learning, building a machine learning model, which we are going to still look at, right? So there are actually a lot of other things we've not looked at yet. So moving forward, we'll be looking at them one after the other. So I urge you to go back to all that we've been doing so far so you don't get lost. Like you don't get lost. I understand that this can be overwhelming for some of us that are entirely new to this, but please and please, there's nothing that is too hard for you to learn. Like once you give it your time and your commitment, you'll definitely be able to pick it up. All right. So this is actually where I'm going to be stopping for today. We've done justice to these three algorithms, KNN, support vector machine, and decision trees. I'll try to make available some resources, some video resources. Class rep, please remind me because sometimes these things just skip my head. So remind me this night. If I don't do it before 9 p.m., please remind me so I upload it. I upload this video as well and I upload the materials so that you are able to go over everything before tomorrow's class. Tomorrow's class, we are going to be looking at some other algorithms as well, which most of them will be building on decision trees, right? Very, very important. So you need to understand decision tree so that tomorrow's class won't give you headache. Okay, so that's going to be it. I'm going to be wrapping up and drawing the curtain at this point. Yeah, so thank you very much for your time, and I'll be taking questions now. So if you have any question, please indicate by raising your hand. Okay, I think there are some things that I actually didn't really look at. So I didn't look at the advantage and disadvantages of each of these algorithm. So you can see quickly, yeah, this material we made available so you can read it. But for SVM, we have advantages here. We have it is effective in high dimensional space. Unlike KNN, which does not perform well in high dimensional space, SVM performs well when you have a lot of features. Okay, it is versatile as well because of kernel functions. So kernel functions allows you to even work with non-linear data. So that is what makes it versatile. It is robust to it is robust against overfitting. So this overfitting is going to be looked at as well. So this is a very important concept too in ML. We're going to look at what overfitting is. All right. Disadvantage of SVM, it's computationally intensive when you're using large data sets. Performance can be sensitive to the choice of kernel and parameters. Less effective on data sets with significant noise. So all these things are just minor details that you have to look at when selecting it. So the same thing goes for decision tree. Advantage is it is simple to understand and interpret. But when you have a lot of features, it might now start to become complex to understand because you can actually look at the decision tree, the nodes, and all of that, and see how it is making the decision for prediction. It requires little data processing, okay, because it can actually it takes a lot of input that it takes input basically that you don't even need to process. It can handle both numerical and categorical data, performs well on large data sets, capable of modeling complex relationships. Disadvantage is prone to overfitting. So this overfitting, you can see it has been mentioned again. Don't worry, you will know what it is in the subsequent classes. It can be unstable because of small variation in data might result in a completely different tree. Does not support online learning. I need to confirm what this means. Right, I think it might be a typo. It's biased towards pictures with more levels, right? So when you have pictures that has more levels, like a lot of categories, so it will pay more attention to those features. So that is going to be it. I think we don't have any other thing in for today's class. So please, if you have questions, just raise your hand. I'll be taking question and be wrapping up immediately after that. All right. Kechika, your hands is up, so please. Okay. I think what this online learning is like incremental learning, right? Once you build a decision tree, you've already built a snapshot of what you need. So when you get new data, it doesn't adapt as well as other algorithm adapts to new data. So online learning is almost the same thing as incremental learning, like introducing new data sets and using it to retrain the model. So yeah, that is basically about. It's just a very minor thing to note, right? So yeah, please you're on mute now. Go ahead and ask your question.
Okay, hello sir. Good evening, sir.
Yeah, good evening.
Okay, I don't know if anybody can hear me.
Yeah, I can hear you loud and clear.
I don't understand what
I can hear you.
Okay, sir. My question is that I don't know. I just want to know if this logistic regression and polynomial regression is one and the same thing. And secondly, are we going to learn about time series?
Okay, thank you. What do you said logistic regression and polynomial. Is that what you said? Hello,
Uh,
hello.
Hello, sir.
Did you say polynomial regression?
Yes, sir, and logistic regression.
Okay. Yeah, so they are not the same thing. Logistic regression is for classification task. Polynomial regression is an extension of linear regression, right? Maybe
Okay.
in cases where you want to fit more complex data that they are not so they are not so linear. Like the relationship is not perfectly linear, but you want to adjust it in a little way to add some curves to your line. So it's actually it's actually quite not so intuitive. But once you have a data set that using a line will not fit it perfectly, you understand, you can add polynomial features to that linear regression model, which will now adjust it a little bit, you understand, to make it fit those curves and all of that. So that is what polynomial regression is. It's an extension of linear regression. You know what polynomials are now? They are all these x raised to power 2, x raised to power 3, x raised to power 4, and all of that. So adding polynomial features to your linear regression actually makes it adapt to non-linear data, right? So that's just an extension. So logistic regression and polynomial regression, they are not the same thing, all right? So you can actually compare polynomial regression with linear regression and just yeah, that one is more comparable than logistic regression. And also for time series, no, we are not going to be learning time series. Time series is a whole lot, is a different thing on its own. Understand? So when you come to data science is a very broad field. Like there are to a lot of things to learn, and it's not possible for us to cover all of them in 3 months. Just Saturdays and Sundays it's not possible. The what we're even covering currently is a whole lot. All right. So the time series is not going to be covered here, right? But if it requires a whole different set of algorithms on its own. So if you're interested in that, go ahead and explore. All right, carry on. Yeah, so that is it for your question. Any other question? So we call it a day. Any other question? All right. So I think we're going to draw the curtain at this point. Um, yeah, it's actually an interesting. It was actually an interesting class. Someone said some of the words I've never heard in my life. See, we all pass through that stage, right? Don't just let this word intimidate you. Like that is how you learn. Everything you know now, at some point in your life, you didn't know them, but now you are very comfortable with them. You can even close your eyes and do them. So just look at it in that from that perspective. You are getting introduced to something doesn't mean you will not know it. It's just exposure. Continue exposing yourself to it and practicing. You'll master it with time. It's not even a problem at all. All right. Okay, so that's it for today's class. I'm going to be wrapping up here. Yeah, exactly. Thank you, Favor. Sometimes things look difficult at first, but once you look through them again, you go realize, say, that is just the approach I want us to have. Like, don't don't see it as hard. Just see it as, oh, this is the first time I'm seeing this thing. So understandably, it will not be intuitive. Like I'm not going to understand it like as something I already know. So the thing is just to check it out again and to just see how it fits with all the other things I know. That is how you build knowledge. You build knowledge, you add things that you learn to things that you already know and you make sense of it in that context. So that's why foundation is very important. If you don't have foundation in some certain things, it will be difficult for you to grasp advanced concept because there is no place you are trying to you can't place what you are learning now on anything that you already know. It is impossible. It's just like putting a square peg on inside a rectangular or a circular hole. It won't fit. So the foundation is very essential. That's why I always emphasize it. Once you know the foundation, fitting in new knowledge will be seamless, will be simple, right? So don't try to jump into knowing the advanced things, right? Try to understand foundation, and you will be able to learn fast, very, very fast, right? It's just taking time. Okay, this is how this one fits into this. Okay, this is how this thing. So that is just it. It is easy. That is just the truth. It's just that this is your first time. It is easy. I'm telling you the truth. It is easy. This is just your first time. All right. So don't get intimidated at all. Like, don't get intimidated at all. This thing is very, very easy. So that's going to be it for today. Thank you very much. And do have a lovely evening. And don't forget to write out what you learned today in the group chat. I really I'm looking forward to seeing what you learned today. All right. So please do that. And thank you very much.